Okay, today is day 2 of differentials. So first we're going to talk about error. So error is the difference in the tangent line versus the original function. So if you kind of look at, and I'm going to show you another picture here, which is also on Canvas. So right here. So here, this yellow line is the original function, and the red line here is the tangent line. So this little piece in between, so like if I'm trying to approximate if I'm using the tangent line, I have this ordered pair. And if I'm using the original function, I have this ordered pair. So the error is the change in the y from the original function to the tangent line. So if you kind of look at it on the y-axis over here, it kind of helps. So you have the point of tangency here at xy, and then we go delta x or dx away from x to get the new point. So here is my y value for the original point. And then if I go on the original function, I'm up here. So that is your change in y. That is the actual y value on the graph. Where if I go up to the tangent line, the red line, and I come over, so maybe I should use red here. So if I come over here, that is the y value on the tangent line. So the difference between the y value on the original and the y value on the tangent line, we call dx, or sorry, dy. And when you go to the original function, so like that's the yellow graph here, if I come over here, the difference of the y values on the point of tangency and the actual graph we call dy. So I kind of drew a kind of blown up picture from the one we talked about yesterday. And here is just a little way to remember. So if you're finding dy, it's the y value on the tangent line minus the y value of the point of tangency. If you're finding delta y, you're doing the actual y value minus the y value of the point of tangency. So that y act with the subscript a means like on the actual function, what is the y value? And then your error is subtracting those two y values. So your y value of your point of tangency minus the y value of the actual function. So again, this picture can be found on Canvas. All right, so going back to our notes here. So again, the difference in, so we're going to say that this is your y value on your tangent line minus your y value, the actual y value. And that is what error is. Okay, sometimes they ask for percent error. If they ask you for your percent error, that is equal to the error over the original. So we might need that later. Okay, so sometimes they will ask you if it's going to be an over approximation or an under approximation. So an over approximation is going to occur when the original function is concave down. So if you see that blue line right here, this blue function is concave down. So then that means that your tangent line will be above. So that red tangent line is above the curve. So when you approximate using the tangent line, it's going to be an over approximation because the tangent line is above. An under approximation occurs when the original function's concave up. So if I have this concave up function, when I draw my tangent line is going to be underneath it, which will make an under approximation. So those are your important things: concave down, concave up. So concave down is over, concave up is under. All right, our first example, we're going to write the equation of a tangent line to this function at x equals 1. Then find the error using the tangent line at 1.5, and then is this an overestimate or an underestimate? All right, so first when we write a tangent line, we need a point and we need a slope. So to find our point, we're going to need to find f of 1. So if you plug 1 into the function, you get 3 minus 2, which is 1. So our point is 1, 1. Your slope is your derivative at 1. So I first need to find the derivative of f, which would be 6x. And then you plug 1 in. So f prime of 1 would be 6. So there's your slope. So my tangent line. So I'm going to put, so y minus y equals m times x minus x. And we plug in that ordered pair of 1, 1 and our slope of 6. And I'm going to put a little t here so that I remember that that's my tangent line. All right, so we want to find the error for using the tangent line at 1.5. So we need to find the y value on the tangent line when x is 1.5. So when x is 1.5, I'm going to have my tangent line, and I'm going to plug in 1.5 for x. So that's y tangent minus 1 equals 1.5 minus 1 is just 0.5, which I'm going to write as 1/2 because that's easier for me to think about. So half of 6 is 3. I didn't leave enough space here, so let's come up here. So y tangent minus 1 is equal to 3. So the y value on the tangent line is 4. Okay, so then remember to find error. If we come back up here, error is the y value on the tangent line minus the actual y value on the function. So that means I need to find f of 1.5. So I'm going to take, and that is going to be, I'm going to label that as y on the actual. Remember, f of x is really y, so I'm going to plug in 1.5 into our function, and that is going to give you 4.75. So that is your actual y value. So to find error, or error is equal to the y value on the tangent line minus the actual y value. So for our problem, the tangent line y value was 4 minus the actual value is 4.75. So that's going to give me 0.75 for my error. So I am off by 0.75. So error is like that distance. Let me go back to that other picture here. This is what we just found. to be 0.75. So the difference between those two is 0.75. All right, so now we want, is this an over or under approximation? So I need to figure out if the original function's concave up or concave down at x equals 1.5. So if you think of, I mean, you can look at our second derivative. So our first derivative over here is 6x. So my second derivative is 6, which means that is a positive number. So that means that f is concave down. So if I'm concave down, oh, sorry. The positive means concave up, not concave down. I apologize. Positive means our original function's concave up. And if you think about it, this is a quadratic that opens up, so it is concave up. So that means when I draw a tangent line, it's going to be underneath. So it's going to be an under approximation. So what we would write here is we would say that it is an under approximation since f is concave up. And that's enough. And we kind of showed with the second derivative that it was positive. All right, our second example here. What is the error in the tangent approximation? So we have this function is y equals the square root of x at x equals 9 and delta x is positive 1. So that means that we're going to go 1 away from 9. Okay, so our original, maybe let's do our original function here. The point of tangency is 9. And then when you plug 9 into the square root of x, you get 3. And then also on the point of tangency, we're going to plug in 10 because our delta x is 1 away. So we're just adding 1 to 9 to get 10. And when we plug that into our original, we get the square root of 10. So those are our two ordered pairs on the original equation. All right, we also need, so we have our point of tangency. This is our point of tangency. And we need a tangent line, so that means we need to find the derivative. So let's find y prime. So this is really x to the 1/2. So that's going to become 1/2 x to the negative 1/2, or 1 over 2 root x. And then to find the slope of the tangency, of the point of tangency, we're going to plug in 9. So 1 over 2 square root of 9 gives me 1/6 for my slope. So my tangent line is going to be y, and I'm just going to put a little t so I remember it's tangent, minus my y coordinate of the point of tangency, which is 3, equals m, and then x minus 9. And then in our point of tangent, or in our tangent line, we're going to plug in, so this delta x equals 1 means that x is turning to 10. So in my tangent line, I'm going to plug in 10. And so my y coordinate of my point of tangency is 1/6 plus 3, which is 3 and a 6, or You can write it as 19.6 or as a decimal 3.16 repeating. All right, and then our next step, because remember we're finding error, so we need the actual y value. So we need y actual, which we already found out. Remember over here was the square root of 10. And the square root of 10, if you put it in your calculator, is approximately 3.16228. So your error is y tangent minus y actual. So my tangent line was that 3 and 1/6 minus the square root of 10. Or if you subtract those two decimals, it's going to be approximately 0.0044. So that is what my error is. And then is this an over or underestimate? So again, if you think about your square root of x graph, that is concave down. So when you draw a tangent line, it's going to be above it. So this is going to be an overestimate. Since square root of x is concave, oops, sorry, is concave down. All right, propagated error is next. So propagated error is an application of finding dy. Use methods learned to find dy, the error. You may use the tangent line and subtract the two y values, or you can use the derivative and cross multiply. So I'm going to show you kind of both ways in one of our examples, or we kind of talked about it a little bit yesterday, but propagated error is basically saying we're going to use dy since the tangent line is so close to the original. So again, if I go back up to this picture here, like if you're really close to that point of tangency, the error is going to be so close to the same y value is going to be essentially 0. It's kind of like the last problem we did, like the error was really like almost 0 the closer you get to the point of tangency. So we can use dy to estimate. Another thing that will come up is that the percent error in volume is the propagated error divided by total volume. So if I want percent error in volume, that is going to be the propagated error. So the propagated error in volume, that means dv, because instead, like I said, dy, y is the function, whatever you're finding. So we're finding volume. So it would be dv divided by the total volume, which is v. The other thing I want you to write down is that if it asks you to estimate, that means we're going to use dy or dv or d whatever they ask you to estimate. All right, so hopefully this will make a little bit more sense when we do this last example. Okay, so the radius of a ball bearing, which is a sphere, is measured to be 0.7 inches. So I'm going to write that down. So R is measured to be 0.7 inches. If the measurement is to be correct within 1 or 0.01 inch, so that's saying that they want delta R, which is also equal to dr, to be within, so it can be plus or minus 0.01 inch. Estimate, so that's that dV, estimate propagated error in volume. So propagated error in volume, when we're estimating, that is saying dV. And percent error in volume means we're going to do dV over V. Okay, so now I see that we need dV, so that means I need the volume formula. So my volume formula is 4/3 pi r cubed. So that is my volume of a sphere. Because it says estimated, we want to find dV. So we're going to go ahead and find, we have V and R, so this would be dV over dr is equal to, we bring that down, so that's going to be 4 pi r squared. And we want dV, so we're going to multiply that dr over. So dV is equal to 4 pi r squared dr. So now we're going to plug in, so let me switch colors here. So now dV is equal to 4 pi. My R is 0.7 inches squared, and dr is plus or minus 0.01. So when you put that into your calculator, leave out pi when you enter that into your calculator and turn it to a fraction. So dV, when you type that in, should come out to be plus or minus 49 pi over 2,500. And that is approximately equal to 0.061575. So make sure that you do get those numbers, like pause the video and type it into your calculator. All right, so that answered the first question. We found the estimated propagated error in volume. Now we need the percent error. So the percent error is dV over V. So we found dV plus or minus 49 pi over 2,500, or you can use that decimal. And now we need to find V. So V is the original volume. So let's go, volume is 4/3 pi r cubed, and RR was 0.7. Again, when you type that into your calculator, leave out the pi, change it to a fraction. You should get 343 pi over 750. So now I can plug that back over here for V. So my V is 343 pi over 750. I don't know if I have that as a decimal. So I don't know what that is as a decimal, sorry. But your percent error, when you put this whole thing in the calculator, obviously you leave out the plus or minus. It gives you 3 over 70, which is approximately, oh, plus or minus 0.0429, I believe. So again, we want to change, that is not a percent. We have to change it to a percent. So you have to move the decimal 2 places. So take that decimal 1, 2. So as a percent is plus or minus 4.29. And if I put it to more places, it's actually 4.2857%. All right, so what does all this mean? So if you think about a sphere, if a machine is building a sphere and there's some error involved, so sometimes the spheres come out exactly at 0.7 inches with a radius of 0.7 inches. Sometimes they come out with a radius of 0.701 inch. So what we just found is the percent that the volume could be off. So like if you're trying to fit a sphere in a machine and you need it to be within, the volume needs to be within a certain thing, you have this constraint to kind of make sure that the spheres will fit into the thing that you're trying to build. So this kind of gives you how much the volume will be off if the sphere is off by that, if the radius of the sphere is off by that much. But realize when you read these questions, just label the things, like label what they are. This 0.7 is R. This is delta R, which is dr. Propagated error in volume is dV. Percent error in volume is this. And sometimes you can figure out how to do the problem when you're stuck just by, using formulas and using what you wrote down. All right, have a good day.